Well, welcome to this video. What we're going to cover today is the application of Little's Law to security screening for entry into a football stadium. What we're most interested in determining by using Little's Law and related equations is the average time a fan spends in line waiting to get screened. Now, if you read the problem description, the stadium's experimenting or going to implement kind of a new screening procedure where they assume all fans enter a single line when they reach the screening area for a gate. And then basically when a security guard opens up, they wave over the first person in the line. So the person that has been in the line the longest. This is a little bit different than most stadium screening procedures where fans self-select the security guard that they're going to stand in line for. We can just assume that caused too many arguments with people jumping between lines. So the stadium's trying to do something a little bit different, a little bit more like TSA security at airports where all the people trying to get to their flights stand in a single line, and then once they get kind of checked off, they get allocated to the different security, different x-ray machines and etc. So you can kind of read the problem description. What we'll talk about first is just kind of modeling this situation, the screening procedure in the screening area as a queuing system. And basically, in order to kind of start modeling this as a queuing system, we need to understand how customers are arriving to the queuing system. So basically, the customers are the fans arriving to the system, and they're coming either from the parking lot or the tailgate or whatever. And then what will happen is when they arrive, they will enter the line, the queuing system area, which we're kind of considering the screening area, the security screening area. They're going to enter the queue, enter the line, waiting for a security guard to open up, and then once the security guard opens up for them, they get to get screened. So the queue itself is just everyone waiting in line for the security guards. The serving mechanism or the servers are each security guard. And then once you go through and once you're served, you can now enter the stadium. So we kind of have at a high level the picture of what the queuing system looks like. And if you kind of read the problem description, we're given a few things about this queuing system. We're given the mean time in order to screen a fan. It's 45 seconds. So basically what this means is once a person shows up, to a security guard, starts the screening process, on average they take 45 seconds to get served and basically be able to enter the stadium. We're also given the rate at which fans enter the screening area. So basically show up to the line to get screened, and it basically says that fans show up at a rate of 10 per minute in essentially the steady state of this queuing system. And then the last thing we're given is basically observations of the percentage of time that a total number of fans are within a security, in the security or the screening area. So for example, if we look at this chart, 21 fans are in the system 10% of the time. So in the system, in the screening area, means 21 fans are waiting in line plus the number of fans served. So we're going to count every fan that is either getting served or in line in this N. So what we need to do, given what we are kind of know about the screening area and the screening procedures, we'd like to be able to use Little's Law to calculate some key parameters. So Little's Law is a very, very powerful result. It is very general in terms of assumptions on the probability distribution of the input process into the queuing system, etc. So it's a really, really nice tool or nice series of equations because we don't have to the queuing system does not have to satisfy a lot of assumptions. So just as kind of a reminder of what Little's Law states, the kind of core Little's Law is that L is equal to lambda W in words, basically saying the average number of customers in the queuing system, or in our case, the screening area, is equal to the average number of customers that arrive to the system per unit time times the average time the customers are in the system. There's a couple related equations, similar derivations. For example, we can apply have a very similar relationship if we focus simply on the queue itself as opposed to the entire system. And remember, the entire system is everyone in line plus everyone getting served. So if we just focus on the queue itself, average number of customers in the queue is equal to the average number of customers arriving per unit time times the average time a customer spends in the queue itself. And then one nice logical relationship is if I look at the overall time in the system, that's going to clearly equal the average time you spend in the queue or in line plus the average your service time. So what's nice about this is we're typically given in analyzing queuing systems, we're typically given lambda, we're typically given mu, or we may actually be given 1 over mu. In this case, we're given 1 over mu. Remember, mu is basically the service rate of a busy server. So we're given 1 over mu is the mean service time. We're given that. It basically says 45 seconds in the problem description. And then we have to kind of get the ball rolling. We need to figure out, well, which of the other parameters, the L, the W, the LQ, or WQ, can we calculate first based on what we are given? And it turns out for our example, we're given the probability distribution of the number of customers in the system. We're given the PNs based on N. And this, if you sum up these numbers across the N's that we're given, they're going to sum to 1 because we never see less than 10 fans in the system or more than 30. So we know the probability distribution of the number of customers in the system. And L is the average number of customers in the system. Or put differently, it's the expected number of customers in the system. So we can calculate the L as kind of the first step in our Little's Law calculations. So besides L being equal to lambda W, it can also be expressed as the sum across N of N times P of N. And that's just kind of the basic, how do I calculate the expected number of customers in the queuing system based on knowing the probability distribution. So in terms of what we are given, this up top, I just kind of ported over from the problem description, the number of customers in the system, and the probability or the frequency that we observe that number of customers in the system. So what we want to basically do is we're summing up the product of n and pn, so we're going to multiply 10 by 0.01, add it to 11 times 0.01, etc. So in Excel, we can use the sum product function of the n entries with the p of n entries. And this is going to give us the expected number of customers in the screening area at any one time. So we see that we end up with 21.03, roughly speaking, number of fans within our screening system. So if we go back to the Little's Law equation, we know L now. We are given lambda in the problem description. We're given that 10 fans arrive in the area per minute. So what I'm going to do in Excel is I'm going to plug in my lambda, so 10 per minute, and then I can use the L is equal to lambda W equation to calculate the average time a fan spends in the screening area. So we're going to kind of reverse the equation. So L is equal to, remember, lambda times W, which this implies that W is equal to L over lambda. So the average time in the system is this 21.03 divided by the 10. So what we're basically saying is, okay, well, the wait time in the system, on average, a fan spends 2.1 minutes in the system. Now we can kind of get the ball rolling. Well, what we really wanted to know is we wanted to know what's the average amount of time the fan spends waiting in line to get screened. So we can use the equation that W is equal to W plus 1 over mu, WQ here. So this is WQ. In order to calculate WQ. So this implies that WQ is equal to W minus 1 over mu. Now we're given 1 over mu, right? If I look on the problem description, the mean time in order to screen a fan is 45 seconds. Okay, so I'm going to plug in some value for 1 over mu. Now this is one kind of critical step. We need to make sure that when we're dealing with time, everything is in the same units. So this 10 for lambda, right? Lambda gives us the arrival rate per unit time. We chose to view the unit time as a minute. We have 10 fans arriving per minute. So we need to express 1 over mu in terms of minutes, not seconds, in order to be consistent and for the calculations to make sense. So we're going to put in a 45 divided by 60 for our mean service time. So 45 seconds is 0.75 minutes. So in order to calculate our WQ now, we're going to have that, we're going to take the W minus the service time. So the average time in the system minus the service time to see that we basically have 1.35 minutes in that each fan on average spends in the line waiting to be screened. So this is under the 1 minute 30 seconds, 1 minute 30 second threshold. So remember, I mean, this is 1.35 minutes. So, you know, in order to get the actual seconds, let's multiply 0.35 times 60 seconds. So we're in the line for an average of 1 minute 21 seconds. All right. So we've answered the main question that we discussed, that we wanted to calculate, but let's kind of close the loop here and calculate all the parameters associated, all the key parameters associated with the queuing system. Last thing is we want to kind of calculate LQ. Well, LQ is equal to lambda times WQ. Right? And so what this implies is that we can take the 1.35 wait time times the arrival time, and we see that we get that the average number of customers in the queue is this 13.53 number. So it's kind of nice. This concludes kind of all the analysis that we're interested in with respect to this queuing system. One thing to kind of comment on in this particular example is that if I look at the number of customers in the system and compare it with the number of customers in the queue, the difference gives me the average number of customers being served at any one point. So average number of customers in the system minus the average number of customers in line in the queue part of the system gives me the number of servers, or the roughly speaking, the average number of people being served at any one time gives us the average number of servers appearing in our system. So the difference ends up being 7.5 between L and LQ. So what we are kind of saying in this case is that we don't always have the same number of servers and the same number of security guards working, which is kind of an interesting observation. So that concludes this discussion of applying Little's Law to the stadium screening problem. All right, I'll see you next time.